So welcome everyone to Securing Network Connectivity with IPsec. My name is Brian McGahan. I'm going to be the instructor for this particular webinar. I am a CCIE in security, as well as a number of other verticals: routing and switching, service provider, data center, CCDE in design. And I've been a CCIE almost 20 years up to this point. So I've been dealing with IPsec for quite a number of years to provide secure network connectivity. And it's definitely still going to be relevant for today's networks for offering security in the transit path between two different networks. So you guys can see my email address there, bmcgahan@ine.com. You can follow me on Twitter at Brian McGahan or on linkedin.com/in/bmcgahan. Any questions that you guys have after the course, please feel free to get in touch with me. I'm more than happy to help for whatever technical questions that you guys have. Okay, so before we get into technical discussion, just a couple of housekeeping items here about the class itself. You can see there's a question and answer box, so please feel free to use that to type in your questions as I'm going through the topics. We'll spend some time at the end taking questions for those questions that I didn't get to during the presentation. And also the class is recorded. So for those of you that need to step away or you want to review this afterwards, there will be a recording that is going to be sent out afterwards. And just check your email for a follow-up email after class for a link to the recording. But otherwise, let's go ahead and get started here this morning. So for today's agenda, we have four main points. First off, what is secure network connectivity? What is IPsec? How do we implement IPsec? And then we're going to go through a Q&A. Okay, so first and foremost, what is secure network connectivity? So our goal as security network engineers or network security engineers is to be able to provide secure channels of communication over insecure networks. And most of the time, this insecure network is going to be the internet, where we have two remote offices that we're trying to connect, or a remote user and a central office that we're trying to connect. And we want to make sure that we have privacy in our data that we're forwarding over the public network. Okay, one point that I want to mention here, though, is that a lot of times the keyword virtual private network is thrown around a lot for different technologies that we have in networking. But one of the key points here is that virtual private network does not necessarily imply encryption. So it does not imply security, just a virtual connection. So for example, an MPLS layer 3 VPN or an MPLS layer 2 VPN, these don't provide encryption. So anyone who is able to grab your packets in the middle will be able to decode that information. So it's typical that in a lot of network designs, you combine IPsec with other VPN technologies. You run IPsec over MPLS layer 2 VPN or over layer 3 VPN or just over the internet. Okay, so why do we need secure network connectivity? We're going to start with a practical example where we're going to do some packet captures and we're going to look at what we can see inside the clear text communication. So if we take a look at our diagram that we're going to be using for today, we have 5 routers that are connected in serial. So router 1 to 2 to 3 to 4 to 5. And our ultimate goal is that we want to provide secure connectivity between router 1 and router 5. The problem with this, though, is that we have an untrusted cloud in the middle of the network. We have router 3, and we want to make sure that router 3 is not able to read our packets as we are transiting those through between router 1 and router 5. Okay, so unfortunately, the end host can't prevent their traffic from being captured in the cloud. This is the ultimate problem that we run into, that once you send your traffic out onto the internet, you really have no control over where it's going to be forwarded or who it's going to be forwarded through and whether they are sniffing those packets as they are going through in transit. So the key point is that anything sent in the clear can be reproduced from a packet capture, even things like phone calls. So you have a VoIP communication that's going between your sites. Someone is able to capture the SIP packets, and then they're able to rebuild this using Wireshark and then rebuild the phone call and actually listen to the phone call. Okay, in today's example, we're not going to go as far as making phone calls, but we're going to look at an example of using Telnet between router 1 and router 5 with a clear text username and password, and then look at how we can grab this information in the middle of the network by doing a packet capture and then rebuild the TCP stream so we can see what the username and password is for the device that was authenticating through us. Okay, so the first thing that I'm going to do in my topology here is enable basic routing. So I'm going to enable EdgeRP on all of these interfaces here. And our goal is that we're trying to get IP connectivity between router 1 and router 5. Okay, so let me just check that all these connections are open. Router 1, 2, 3, 4, 5. And we're going to send to all of these sessions router EdgeRP1 network 0000. Okay, let's make sure we're logging console 7 and logging is on. And let's look at the show IP route EdgeRP. Okay, ultimately what we should see here in a second is that we're going to be learning EdgeRP routes from router 5's point of view, and we should be learning the loopback interface of 1111. Show IP EdgeRP neighbors, show IP interface brief, show IP EdgeRP neighbors, show IP interface brief. Okay, so some of these interfaces are shut down automatically by default. Interface range gig 124, no shut. And I do have the file that I'm working on, the CML.YAML file. So anybody who wants to follow along after the class, you'll have an option to do that if you want to load the configuration into your own CML instance, or if you use the CML instance under the DevNet sandbox, you can go ahead and play around with this particular example. Okay, so let's look at the show IP EdgeRP neighbors. We should be able to get EdgeRP adjacencies now between these 4 devices. Let's look at the show IP route EdgeRP. Okay, we're in the process of converging still. And we have the address 1111. Okay, so going between 5555 and 1111, those are the loopback interfaces of the routers. If we do a trace route to 1111, source interface of 5555, we can see that we're transiting over router 3, who is the untrusted device in the public cloud, essentially. We can say that this is like the internet. Okay, so we have the packets where we have reachability between the endpoints. Next step is that we're going to telnet from router 1 to router 3 and log in, or from router 1 to router 5, I should say, and log in. So let's go ahead and create a username. Username Brian, password Cisco 12345. Under the VTY line, we're going to say login local, and transport input is telnet. Okay, so on router 1, if we telnet to 5555 source loopback 0, we're going to log in as Brian and password Cisco 12345. Okay, so nothing too complicated yet. We're just testing basic connectivity and testing connectivity with telnet as the upper layer application. Okay, the next step is that we're going to do a packet capture on router 3, and we're going to follow the TCP stream that's going between router 1 and router 5 in Wireshark, and then see if we can decode the username and password that was entered as router 1 logs into router 5. So let's go over to our hypervisor, which in this case is CML. So I'm going to go to the link that goes between router 2 and router 3, and I'm going to do a packet capture on this particular link. Okay, so let's go ahead and start our capture. And then let's do another telnet from router 1 over to router 5. Login as Brian, password Cisco 12345. And we should see the telnet data in the packet capture that's coming from router 3. So let's go ahead and download the packet capture. And we see first off, we have the 3-way handshake that's going between router 1 and router 5. So this is in the clear. We have the SYN, followed by the SYN ACK, followed by the final acknowledgement. And then we have the actual telnet data. Okay, so we're going to right-click this packet and we're going to follow the TCP stream. And what this is now going to show us is basically the clear text version of what was the payload of those telnet packets. So we can see the username login as Brian. It's echoing the characters back. And then the password, which was hidden previously, we can see it now in clear text as Cisco12345. So this is the main motivation then of why we need secure network connectivity, is that once we send the packets out onto the internet, we don't know who they're going through, and we don't necessarily know who can capture the packets and then rebuild them into some form that they would be able to get our private data. Okay, so how can we prevent this? How can we provide secure network connectivity? Mainly, there's going to be two protocol suites that we would be looking into, either SSL and TLS or IPsec. Now, SSL is typically used for host-to-host VPNs, like your web client connecting to your web server and then negotiating it on demand as they're downloading a web page. But SSL can also be used for remote access VPNs, like the Cisco AnyConnect VPN client, that allows a simple way to implement a VPN over the web ports. Okay, whereas IPsec is typically going to be used for site-to-site VPNs. So, for example, we have a remote site that's trying to talk to the data center, and we're trying to create a permanent tunnel that we're going to use for communication between us and the data center site. This is where our focus is going to be for today. Okay, technically, IPsec could also be used for remote access VPNs. There is a way to do dynamic IPsec, but since we have just an hour to talk about this today, we're going to talk about just static tunnels between two point-to-point sites. Okay, so we talked about what is secure network connectivity. We looked at the case where we can capture clear text frames in Wireshark if they're not IPsec encrypted. So next, we want to know what is IPsec and why would we want to use this in order to perform network security. Okay, so in general, IPsec is a security suite. It's a suite of open standards protocols that allow us to provide secure VPNs by offering both authentication and encryption of the IP packets between two or more IPsec peers that are reachable over an IP transport. So some of the key points here: IP transport means that we don't have any special requirements about how we are sending the packets between the TCP or between the IPsec peers. As long as we can ping between the peers, then we should be able to form an IPsec tunnel. Okay, the other thing that's important is that we offer both authentication and encryption. So we can tell where the packet is coming from, and we can tell that no one can read the payload of the packet as it's actually transiting through the network. Okay, the other thing that's important is that it's open standards based. So multiple vendors implement IPsec, and their implementations should be compatible with each other, that we have inter-vendor interoperability, because it is part of an open standard suite of RFCs that defines how IPsec is supposed to work. Now, why would we want to use IPsec versus some other solutions like using an SSL VPN? The main reason that is IPsec has four main security services, or it has four main features that we're concerned about. Okay, the first is confidentiality, meaning can someone read my communication in transit? So if they grab the packet, can they look inside the payload and see what information is inside there? We have data origin authentication, meaning did the data come from the legitimate source? So if we think that the remote user is Brian, we want to make sure that we have some sort of authenticator, like a password, for example, to make sure that we have the correct device that is actually sending us the packet. The data integrity is to check if someone is modifying the packet in the middle of the network, like someone's trying to do a man-in-the-middle attack. And then lastly, we have anti-replay, which is to check if we had already received this packet in the past. So if someone is capturing, let's say, like a checkout process and they're doing a refund, we don't want them to be able to capture the refund and then replay it over and over and over and then exploit the online store, for example. Okay, specifically, the way that IPsec works is that it uses symmetric encryption. And symmetric encryption means that we use the same encryption key as we do for the decryption key. So we run into kind of a chicken and the egg problem here, that we want to encrypt the communication between two or more users, but we don't have a way to exchange the key without people listening to the communication in the middle between the two peers. So how can we exchange a secure key over an unsecured network? The way specifically we're going to do this is with two types of negotiation. We call them phase 1 and phase 2. Okay, phase 1 is where we're creating a secure tunnel to exchange our encryption and decryption keys over. And then phase 2 is when we're actually encrypting and decrypting the packets with the shared key. So the first portion of this is what we call the Internet Key Exchange, or the Internet Security Association and Key Management Protocol, either IKE or ISACAMP, where ISACAMP is the framework and IKE is the actual implementation. So the goal here is that IKE is used to negotiate a secure channel to exchange the IPsec encryption and decryption keys. So we have basically two devices that want to run IPsec, but the network in the middle is unsecure. We're assuming that someone is capturing the frames as they're in transit between the two peers. So we need some sort of methodology that we can exchange the secure keys over the unsecure medium, and that's what IKE is going to do for us. Okay, specifically, IKE runs over UDP port 500, so it is network address translation friendly. Or it is firewall friendly. Like if you have an active firewall that's inspecting packets, you can go from the inside to the outside with UDP port 500 and then return your flow on the opposite direction. And IKE has two versions, aptly named IKE version 1 and IKE version 2. So how phase 1 works is that the IPsec peers are going to negotiate what we call an IKE Security Association, or an SA. And during the negotiation of the SA, we have a bunch of variables that we need to agree upon before we can move on to the next phase, which is the IPsec negotiation. Okay, specifically, these are going to be the authenticator, the hash, the encryption algorithm, and then what we call the Diffie-Hellman group. Okay, the authentication could use a pre-shared key, or it could use certificates. So if you have your own certificate authority server, you can register your IPsec peers to that CA, and then you could use certificates as a type of authenticator, or you could just have pre-shared keys where everyone is sharing the same password for the phase 1 authentication. Okay, hashing is going to be done with either MD5 or SHA. It's not recommended to use MD5 anymore because there are some vulnerabilities that are available to attack the MD5 algorithm, what we call the rainbow tables, or pretty much pre-calculated results of MD5 that you can search through and see if you can find your key that matches up with the MD5 hash. So SHA-1 or SHA-256, SHA-512 is recommended over MD5. Okay, for encryption, we could run the digital encryption standard or the advanced encryption standard. It's not recommended to use DES or triple DES anymore. Those are considered compromised algorithms. It is recommended to use AES and a longer key length, like 256 bits for our encryptor. Okay, then lastly, we have what we call the Diffie-Hellman group, where the Diffie-Hellman group is going to be the method that the two parties are going to exchange the key over an insecure channel. So this is the specific algorithm that we use where someone is sniffing the packets in the middle. We need to come up with some sort of password, a shared secret between the two peers, but we need to make sure that no one in the middle is able to derive the key that we're going to be using for encrypting and decrypting the packets. So this is what the Diffie-Hellman exchange specifically does. So you can see I have some links here for more information. If you want to see how the Diffie-Hellman exchange specifically works, there's a good article on Wikipedia that goes through this in kind of plain language, talking about Alice and Bob, that they're trying to generate the shared secret keys, and then what is the math behind the algorithm that allows them to actually generate these keys. Okay, specifically what we need to configure is what we call the Diffie-Hellman group. Diffie-Hellman group is going to control how large of a prime number that we are generating, where it's not recommended to use Diffie-Hellman groups 1, 2, or 5 anymore. There are some attacks on the DH process itself, but if you're using larger key lengths like 2048 bits, then generally that's considered to be computationally infeasible for someone to break the exchange for the keying information. So the general attack against IPsec is not against the encryption itself. It's against the exchange of the encryption and decryption keys, and then you can read in the clear any of that data that is going across the IPsec tunnel. Okay, so for phase 1 today, IKE version 1, Diffie-Hellman groups 1, 2, and 5 are considered compromised. There's an attack against them called the logjam attack, which basically you take a large computing resource like a supercomputer or just a very large cluster of CPUs, and you can pre-calculate the computationally large section of the attack, basically what is the prime number. Then the individual logarithms that you need to solve the rest of the problem, those can be done on commodity CPUs within a minute or so by combining them with the pre-calculated information that your large cluster is forming. So the recommendation is to use Diffie-Hellman group 248-bit or higher, or to use elliptic curve, which is another variation of the cryptography that's used in the Diffie-Hellman exchange. Okay, but we'll see what we're going to configure today is called IKE version 2, and IKE version 2 addresses this problem in the Diffie-Hellman exchange, and it addresses other problems like denial of service attacks against the IKE process itself. Okay, so when we look at IKE version 2 versus IKE version 1, IKE version 2 is going to simplify IPsec negotiation by having less initial messages needed to establish the tunnel. Okay, this means the tunnel is going to come up faster. We have less latency or less delay for the tunnel initiation when we're comparing IKE version 2 versus IKE version 1. Okay, also IKE version 2 simplifies the IPsec standards, where everything is combined now into just one document. So for example, previously NAT traversal was its own RFC. Now it's combined inside the IKE version 2 standard. So it simplifies the inter-vendor interoperability that it specifies exactly how we're going to do this with IKE version 2. Okay, also IKE version 2 supports newer hashes and newer ciphers, what we call Suite B cryptography. So these are going to be the new AES standards, the new SHA standards that are going to be for better encryption, better hashing, that are recommended to be used because we have the potential where the Diffie-Hellman groups 1 through 5 were compromised, and we don't want to use those anymore. We want to use the larger key lengths. The same with MD5, that we would prefer to use SHA-1 or SHA-256, SHA-512, because of the potential issues with it being compromised. Okay, last but not least, IKE version 2 supports asymmetric authentication, which means that I could challenge you with a pre-shared key and you could respond with a certificate. This is useful in remote access situations where you could have your remote users using a pre-shared key and then your VPN server using a certificate. Whereas in IKE version 1, if I was using a pre-shared key, you had to use a pre-shared key. If I'm using certificates, you have to use certificates. But in IKE version 2, we can have asymmetric authentication. Okay, so once we get through the phase 1 negotiation, what we're left with is the encryption and the decryption keys that we're going to be using for the actual IPsec data plane. So phase 2 negotiation is now going to begin. So IPsec negotiation, and there's a number of other attributes that we need to exchange in phase 2 negotiation. First, what we call the proxy identities. Okay, this is going to determine what traffic is being protected. And this is one of the differences between what we call a route-based VPN versus a policy-based VPN. So policy-based VPN could say, I want to encrypt traffic from subnet A to subnet B, but only if it is clear text web traffic like port 80. So you can get very granular as to what type of traffic that you want to encrypt, or you could be more general and just say any IP packet that goes out this interface, that goes out tunnel 0, is going to be encrypted with this particular transform set. Okay, we then have the security protocol, which is either authentication header or encapsulating security payload. The difference between these is whether we want to do just authentication or whether we want to do authentication plus encryption. 99% of the time we want to do encryption, so we're going to be using ESP as opposed to AH. AH has very limited applications in the case of VPNs because it does not support encryption. Okay, we then have the encapsulation mode, either tunnel or transport, which I'll show in a minute, the difference between the actual encapsulation of the data. Hashing, are we running MD5 or SHA, which again, it's not recommended to run MD5 anymore. Our encryptor, the cipher, is it DES, triple DES, or AES, where again, it's not recommended to run either DES or triple DES anymore. And then we have some optional parameters like perfect forward secrecy and the lifetime of the tunnel in either bytes or in time. Okay, now I mentioned the difference between authentication header and encapsulating security payload between AH and ESP. Main difference is that AH supports authentication only, ESP supports authentication and encryption. So because of that, ESP is going to be our de facto standard for IPsec VPNs. We're not going to be using AH in our examples. Okay, for the encapsulation mode, we can run in either transport or tunnel mode, where the difference between them is that in transport mode, we leave the original IP header alone and either authenticate or encrypt just the payload. Whereas in tunnel mode, we're adding a new header on the outside, a new IP header on the outside, and then we're encrypting or authenticating the entire original IP packet that's going between the IPsec peers. Now, in the vast majority of cases, we're trying to send private data over the public network. And it's very likely that we're using private addressing like the RFC 1918 space, the 10 network, 172.16.31 and 192.168, which means that that is not routable via the public internet. Okay, because of this, the de facto standard for IPsec VPNs is going to be that we run in tunnel mode. Okay, because we're typically trying to connect networks with private addresses over the public internet or over public transport. That's why we want to run in tunnel mode as opposed to in transport mode. Okay, so here we have an example of a visualization of transport mode versus tunnel mode. So we can see in the top transport mode, we have only one IP header, and we're authenticating and encrypting just the payload. So we're encrypting the TCP payload and the TCP header. Whereas if we're running in tunnel mode on the bottom, we have a new IP header that's added onto the top, and we're encrypting and authenticating the entire original IP packet. Okay, so once we're done with phase 1 and phase 2 negotiation, we should be left with 3 security associations that represent our negotiated parameters. We should have 1 security association for phase 1, which is going to be the IKE or the ISACAMP SA, and then we should have 2 unidirectional IPsec security associations, one going outbound to the peer, one coming inbound from the peer, where we are negotiating our hashing, our encryptor, the lifetime of the session, and so on and so forth. And then we use what we call the security parameter index, or the SPI, to uniquely identify the IPsec security association between the 2 IPsec peers. Eventually, we have the lifetime expire, so either the lifetime in seconds or the lifetime in bytes. And we go through a process that we call rekeying. Okay, rekeying is when new symmetric keys are going to be created for either phase 1 or phase 2. Okay, and the default behavior is that we're going to take our original Diffie-Hellman exchange and we're going to generate new keys based off of this. So your new key is based off the previous key with the default behavior. Okay, if we enable the feature that's called perfect forward secrecy, this means every time we rekey, we will rerun the Diffie-Hellman exchange and we'll come up with brand new keying material. Okay, so for additional security, you would want to run perfect forward secrecy, but this is going to be at the expense of more CPU cycles. So depending on how many tunnels you're terminating on an individual box, if you're talking in the order of thousands, then you might have a problem running perfect forward secrecy where your CPU becomes too high when you're rekeying multiple tunnels at the same time. But otherwise, if we have just one tunnel point to point, we should be able to run perfect forward secrecy without running into any problems on the CPU. Okay, so we talked about the background of IPsec. Now let's get into the actual implementation. We're going to look at some examples on the Cisco iOS command line. Okay, before we get to that though, we need to talk about the difference between the route VPNs, route-based VPNs, and policy-based VPNs. Where in policy-based VPNs, the IPsec peers are going to exchange their proxy identities during phase 2 negotiation. Okay, the idea here is that we're going to say, I want to encrypt, for example, subnet A to subnet B. Then on the reverse end, that peer would say, I want to encrypt from subnet B to subnet A, that the proxy identities are mirror images of each other. Okay, in iOS implementation, this is the crypto map. So crypto map is considered to be a legacy configuration construct. It's not really recommended to use the policy-based VPNs anymore because the syntax has been simplified with the route VPNs, route-based VPNs, where we're using a virtual interface. Okay, the difference between them is that in policy-based VPNs, we don't support dynamic routing protocols, but in a route-based VPN, we could run OSPF, EHRP, BGP, static routing, whatever routing protocol that we want across the IPsec tunnel and form an adjacency inside the encrypted tunnel. Okay, so this is going to be our focus for today, where Cisco iOS calls this a virtual tunnel interface. It calls it a VTI. This is the example that I'm going to show today for two peers that are running virtual tunnel interfaces. Okay, so in general, we could break the configuration steps down into three main points that we need to do. We need to define our phase 1 policy. We need to define our phase 2 policy, and then we need to configure the tunnel interface. Okay, the phase 1 policy is going to be based on some modular configuration of IKE version 2, where we have the IKE version 2 proposal, the policy, the key ring, the profile, and then ultimately the crypto IPsec profile. So it can get confusing when you're looking at the final configuration of this, of how everything is going to fit together. But we're going to look at this as a step-by-step configuration here and see if we can piece this together. Okay, so specifically what we're doing here is that we're going to form an IPsec tunnel between router 2 and router 4, and then we're going to run OSPF over it. Okay, so we're already running OSPF on the inside interfaces. We're running BGP between router 3 and the internal network. Okay, this is getting us IP connectivity between router 2 and router 4. And then once the tunnel comes up, we're going to run OSPF on top of the tunnel, which is going to get us reachability to our internal network. So the router 1 has reachability to router 5. Okay, so my first step here is that I'm going to get rid of the previous EHRP routing config so that we have some segmentation in the network. So no router EHRP1. On router 1, if we look at the show IP route, right now we're learning some OSPF routes. We have 2222 as an OSPF intra-area route, and we have a default route as an OSPF external route. If we go to ping to 5555 source loopback 0, right now we don't have connectivity to 5555. The reason why is that the device in the middle, which is router 3, the untrusted cloud, does not have a route to the 192.168 network, which is what we're trying to protect. So what router 3 in the middle does have reachability to is the link that goes over to router 2 and the link that goes over to router 4. So between router 2 and router 4, we should have connectivity on those outside interfaces. So on router 2, if we ping to 10.100.34.4, we can reach the other end of the where we're going to form the IPsec tunnel towards. Okay, so let's start on router 2 now that we have IP connectivity working. We're going to start with our crypto IKE v2 proposal. Okay, so we'll say IKE v2 proposal 1. It says IKE v2 proposal must either have a set of encryption algorithms other than AES GCM, an integrity algorithm, and a Diffie-Hellman group configured, or encryption algorithm AES GCM, a perfect or a pseudo-random function algorithm, and the Diffie-Hellman group configured. Okay, so this is where we negotiate those 4 variables, which are going to be the encryption, the Diffie-Hellman group, the integrity checking, which is going to be SHA or MD5, and then what they call a pseudo-random function, which is going to be another hash, either SHA or MD5 for generating the keying material. So really, as long as we match this on both ends, that's what the ultimate goal of the phase 1 policy is, that we have equal negotiation of the tunnel. Okay, so first we have our encryption. Encryption, we'll say that this is AES CBC -256. Okay, so you have 2 variations of this, CBC and GCM. We're not going to get into the actual cryptography behind the scenes, but the GCM mode, I believe, is the more secure version versus CBC. Okay, the type of algorithm that it's using. We have the encryption listed, then we're going to have the integrity check. Okay, either MD5 or SHA, so we'll say SHA-512, we'll say the longest bit length available. The Diffie-Hellman group, so we're going to say group 14, which is 2048 bits, group 14. And then the pseudo-random function, SHA-512, I think is the default for this. Okay, so let's do show run section IKE or IPsec. So we have our encryption, we have the integrity, the Diffie-Hellman group, and then the pseudo-random function is SHA-512. It doesn't show up there because that's the default value. Okay, next step is that we're going to have our crypto IKE policy. So we have the crypto IKE v2 policy. We'll say this is IKE v2 policy 1. IKE v2 policy must have at least 1 complete proposal attached. Okay, so the proposal was called IKE v2 proposal 1. And if we look at the other matches here, what we can do is to bind the IKE to a local address. So if you don't want to listen on all interfaces, if you want to listen just on your loopback, for example, you can specify that as the local address. The other option is that we can match the front door VRF, the FVRF, if you're doing VRF aware IPsec. So the idea there is that your WAN link would be in VRF underlay, and then your other interfaces would be in the global VRF or VRF overlay that you're using inside of the tunnel. In this example, we're not doing VRF aware IPsec, so we can just leave this statement off. So if we do show run section IKE or IPsec, okay, we have the IKE proposal 1 called from the IKE policy. Next thing is we're going to define our pre-shared keys. So we're not doing certificates in this example, we're just doing pre-shared keys, which is going to be kind of a more common implementation. So this is going to be defined as the crypto IKE v2 keyring. Okay, we'll say this is our IKE v2 keys. We specify the peer's name, so I'll say this is R4. We specify the peer's address. So in my case, it's 10.100.20 or 34.4. And it also gives you the option for a wildcard mask that you could match any, or you could match like an individual subnet. In my particular case, I'm matching the exact peer address, 10.134.4. And then we specify the pre-shared key. Okay, we'll say Cisco 12345, capital Cisco. Okay, next step is that we're going to call the key ring from the IKE profile. So let's do show run section IKE or IPsec. We have our proposal, we have our policy, we have our crypto key, our pre-shared key, and we're now going to define the crypto IKE v2 profile. IKE v2 profile. IKE v2 profile 1, we'll call this. It says an IKE v2 profile must have a local and remote authentication mechanism and a match identity or a match certificate or match any. Okay, so under the IKE profile, this is where we're going to specify who is the remote peer. So we're going to match the identity of the remote peer. They're coming from IP address 10.100.34.4, mask of all 255, so exactly that address. Okay, next we need to specify what is our authenticator. So the authentication, local authentication mechanism is pre-shared keys. The remote authentication mechanism is also pre-shared keys. What is the pre-shared key, which is the key ring? Key ring is going to be a local key ring that we called IKE v2 underscore keys. Okay, so if we do show run section IKE or IPsec, we again have the proposal, which is specifying our 4 options. The IKE policy calling the proposal. We have the IKE key ring that is our pre-shared key. Then the key ring is called from the IKE profile. Okay, next step is we need to define the phase 2 parameters. So how are we negotiating IPsec? This is going to be the crypto IPsec transform set. So crypto IPsec transform set, we give it a name. We'll say that this is AES 256 SHA-512. And this is where we choose, are we doing authentication header or are we doing encapsulating security payload? And then what variation are we doing of the authenticator or the encryptor? So the encryption, we're going to run 256-bit AES. And for our authenticator, we're going to run SHA-512. Okay, then we have the mode. Mode either transport or tunnel. Default is mode tunnel. So we're going to add a new IP header on top of the encapsulation when we send the packets out the IPsec tunnel. Okay, we now form a crypto IPsec profile. IPsec profile 1. And from here, we call both the IKE profile, set the IKE v2 profile, and the transform set. So the IKE v2 profile, do show run section IKE or IPsec. Okay, this is IKE profile 1. Set transform set AES 256 SHA-512. Okay, if we show run section IKE or IPsec, this is going to be close to the extent of our negotiation config. So we have our phase 1 parameters, which are IKE version 2. We have the phase 2 parameters, which are IPsec, and then we're combining them together in the crypto IPsec profile. saying we're using this encryption, we're using this authenticator for the actual data plane. For the negotiation, we're using this particular profile. Okay, last but not least, we need a tunnel interface. So tunnel interface is what is going to get us to 10.100.34.4, which is the remote peer. So we'll say interface tunnel 0. We're going to give it a new subnet. So we'll say IP address is 192.168. We'll say 24. So between router 2 and router 4.2. We need to specify where is the tunnel coming from. 10.100.23.2 is my local address here. Tunnel destination is 10.100.34.4. So between router 2 and router 4. Okay, I then need to say the tunnel mode is IPsec over IP version 4. Okay, we could also encapsulate it over IP version 6. So you could run 6 in 4. You could run 6 in 6. You could run 4 in 6 even. In this case, we're doing IPv4 routing though. And then last but not least, we have the tunnel protection IPsec profile. Okay, and what do we call the IPsec profile? Is IPsec profile 1. Okay, and lastly, we're going to run routing on this interface, IP router OSPF1 area 0, or IP OSPF1 area 0. Okay, now the IPsec configuration is very template driven, that you need to make sure the parameters are matching between the multiple endpoints in order to form the tunnel. So what we're going to do now is basically just show run on router 2, copy this out to Notepad, and then we're going to change it around in order to match the other side. So let's say show run section IKE or IPsec, and then show run interface tunnel 0. So let's copy this out. And let's start at the top and talk our way through this. So we have the IKE proposal that needs to match between the two peers. We have the crypto keyring, which is going to specify the peer address as router 2. Okay, because now we're coming from 4 back to 2, we need to swap these values. So we're going to say the address here is 23.2, which is router 2's interface facing towards router 3. Okay, we're using the same pre-shared key. Under the IKE v2 profile, we have router 2's address. Then under the tunnel interface, we have a new IP subnet, or new IP address, 192.168.24.4. And then we're reversing the tunnel destination and the tunnel source. Okay, so once you build the skeleton of the config, you can basically use this just to copy and paste to the other nodes. Okay, so almost immediately the tunnel interface comes up, and we now have a new OSPF adjacency on the link. So if we look at the show IP OSPF neighbors, router 4 is adjacent with router 5 and with router 2. And on router 2, we show IP OSPF neighbors, we're adjacent with router 1 and with router 4. Okay, so the point being is that the routing over the tunnel is working. This tells us that both our phase 1 and phase 2 negotiation is successful. Now, in terms of verifications for this, most of these are going to be show crypto IKE v2 or show crypto IPsec. So to look at the phase 1 negotiation, we're going to say show crypto IKE v2 SA for security association. We can see the specific details of how we did the negotiation between the peers, and then we can see that the status is ready. Okay, we have our local address, we have the remote address. 500 means UDP port 500, which is our transport. Okay, so this is the correct output for the phase 1 negotiation. For the phase 2 negotiation, we look at the show crypto IPsec SA, and it says we have our local address 10.123.2, and we're both encapsulating and decapsulating packets on the tunnel. Packets are getting encrypted and decrypted. They're getting digested and they're getting verified. So the encryption and the hashing is working on the packets. Okay, how is it specifically doing this? If we look down a little bit further, we should have an inbound security association and an outbound security association. So if for some reason these don't form, it means that your phase 2 negotiation wasn't working. So in phase 2, we have the transform set ESP 256 AES. So that is our encryptor. And then our authenticator SHA-512 is running the digest. And we're running in tunnel mode for the encapsulation. Okay, same is true on the reverse manner. We have our security parameter index. So this is basically just the sequence number telling us what particular sequence number that we developed during the negotiation. So if we have multiple tunnels between these two peers, we would be able to tell the difference between them by using the security parameter index. Okay, so now let's look at what changed from the perspective of router 3. So previously we were able to capture the packets, and we were able to look inside the payload and look at the telnet password. So we're going to do the same thing again now here. So from router 1, we should be able to ping to router 5 now. Okay, the reason why is that we have that as an OSPF route. Okay, OSPF is running over the tunnel interface. And we should be able to telnet to 5555, username Brian, password Cisco 12345. Okay, so let's go to the CML interface. We're going to capture on the link between and we're going to telnet username Brian, password Cisco 12345. And now let's look at this in Wireshark. Okay, we see now between router 2 and router 4, which are two IPsec peer addresses, the 10.100.23.2 and 10.100.34.4, we are sending packets back and forth between these two endpoints, but the difference now is that the protocol is ESP as opposed to being the telnet or the pings or whatever the inner payload is. So if we look in the IP header, the only thing that this is going to tell us is basically what is the payload protocol number 50, which is encapsulating security payload. And then if we look inside ESP, there's really nothing that we can tell from inside the data what is going on with the actual transmission of the packets. So we know that it's an ESP tunnel between router 2 and router 4, but since it is encrypted with AES and it's being hashed with SHA-512, we're not able to actually read what's inside of the communication. Okay, last example I want to show is the negotiation of the tunnel itself. So we're going to go to router 2 and we're going to shut down tunnel 0. then we're going to capture our packets again and no shut the tunnel. Okay, so what we should see here is the ISACamp exchange. So we see ISACamp is encapsulated as IP, UDP, port 500, source port and destination port 500. And then we have Internet Security Association and Key Management Protocol ISACamp. So this is our IKE exchange, the Internet Key Exchange. We have the security parameter indexes. We can see in the payload, encryption, and authentication, we have encrypted data. So we're not able to see specifically what is happening when they are doing the negotiation. So even if we capture these packets, we're not able to derive the IPsec keys without breaking the Diffie-Hellman exchange. So again, you could use that logjam attack against low bit length tunnels, and then you can compute the logarithm answer and figure out what is the prime number. And then from there, you can derive what are the pre-shared keys, what are the encryption and decryption keys. But if you are constantly rekeying and changing the encryption decryption keys, then this is going to be just another level of security that you have in there that is going to prevent someone from eavesdropping on the communication. Okay, so let's recap our config here. We show run section IKE or IPsec. We have the IKE proposal, which is going to be the 4 options that we have for phase 1 negotiation. Okay, one of those options is doing the authentication. So authentication is pre-shared keys for local and remote, which is called from our key ring. So this particular peer is using this particular key. So the configuration here is modular, meaning that you can add more proposals, you can add more keys, and then you would have separate IKE policies, or excuse me, separate IKE profiles for your different tunnels. And they would specify the remote addresses that you're trying to do the negotiation with, and then what are the subparameters that we have on there. Okay, we then have the crypto IPsec transform set. This is specifying the encryptor and the authenticator for phase 2 for the actual data plane. And this is what we have encapsulated inside ESP when we captured those packets on router 3 and looked at, we weren't able to see inside of the payload. Okay, we then have the IPsec profile. The IPsec profile is calling the transform set and the IKE profile. And then finally, we have the tunnel interface. Okay, questions, guys, on what we talked about here so far with secure network connectivity using IPsec? Okay, so in the appendix of the slides here, here's some references for you if you want to look up the specific details of the implementations. We have the standards for ISACamp, IKE, and IKE version 2. And then for the authentication header and for the encapsulating security payload. So it's a number of different RFCs that combine together to make the entire IPsec suite. IPsec is not just one protocol, it's the negotiation plus the data plane, the phase 1 and the phase 2. Okay, there's a question, do we need to adjust the TCP MSS because the effective MTU is reduced? It's a good idea to do that in your practical designs. So the question here is, if I was to ping 5555 and say the size is 1500 bytes and set the don't fragment bit, we get capital M back which means that we must fragment. So if you go down a little bit further, let's say 1460 still is too big because of the encryption overhead. Let's say 1440. 1420 or 1430. So somewhere around 80 bytes, give or take. And it's going to depend on the input to the encryptor, what the output size is going to be. But it is, there is overhead for the encapsulation that you need to take into account for your other applications. So it would be a good idea to say, if our, let's say our IP packet size, IPMTU is 1400 bytes, the bytes for your TCP header, and then you have your payload size. What is the maximum segment size? So it's not 100% required because fragmentation will occur, but you ideally don't want to do fragmentation when you're dealing with IPsec because it is very CPU intensive to do the reconstruction of the IP packets. You want to offload to the end host, which is what the TCP adjust MSS is going to help you with. So good question there. Okay, any other questions on what we talked about here today with IPsec? Okay, so I'll leave the Q&A box open for a couple more minutes if you guys have any other questions. But otherwise, this is going to be the extent of what we're covering today for this webinar. Thanks, guys, for coming out today. I appreciate you attending. I hope you enjoyed what you saw. The recording for this will be available later if you want to review. And the link to the file share is in the chat window there. Let me post it again here. That has the diagram, the slides, and then the initial configuration file for CML that I was using for building this topology. So thanks again, everyone, for coming out. I hope you enjoyed it, and I hope to see you back for further webinars, further boot camps, further courses here with us at INE. Thanks, everybody.